I'm Gunnar Newquist, and I am from the neuroscience realm. And I started a company once upon a time, and the thesis was that neuroscience could really help bring us the beings that we were looking for. And so this talk is about some of the scientific things that need to happen that I am trying to discover myself and then have others discover and go forward through the future in order to bring real robots to life in a positive way for the world here. And so my background's a little different probably from a lot of people in this field. So I've done a lot of things. I've had about 5 or 6 lives, I think. First, I was a pianist and a biologist. That's how I paid for school. And I did a concert piano major. So I played piano all over the place. And then I moved to Tahoe, California, which is a big ski area, a mountain area of California. And I became a professional extreme skier. And so on the left, you can see the cover of a book. I have some records, including a world record that I can't quite claim because it wasn't entirely legal. But I have some stunts that have not been repeated in 20 years. So I have that to show for my extreme skiing career. After that, I became a research scientist in the neurosciences. This is back when I was cool, I guess. I had a mohawk for a little bit. And at that point, I first started with brain development. I was really interested in the brain and spinal cord development to see if I could help fix things like broken spinal cords, because I had seen a lot of injuries through my days as a skier. And then while I was doing that, I really got interested in looking into robots. I was looking across from neuroscience and thinking about learning and memory and development, and saying, like, why aren't all these principles going towards robots? So I dove into technology and started a company where I was trying to bring these beings to life. Unfortunately, had a financial problem and had to set that company down. And so I went to work for other people in technology, self-driving vehicles, laboratory automation, and I was a product manager for those companies. So today, I also have 2 kids. One of them spent a year in France with me, the older one, when I did a postdoc on learning and memory. At the USPCE Paris Tech. And today I really am jumping back into the business again, trying to build robots that actually create human connection. And so this whole culmination of doing all these different careers, I guess, is me saying, well, I think it's time that we try to connect humans better. Let's build a robot again. So with that, I'll give you a little bit of an idea of where this idea came from. So while I was in my PhD, I worked with a man named R. Alan Gardner, who had cross-fostered chimpanzees in the 1960s. So he was already very ancient by the time I met him. And so he had spent several decades working with chimpanzees and other aspects of how we learn. And through this, I had no idea about behavior at the time. I was mostly interested in development and the molecular sciences. And he really showed me something different I had never seen before. They actually cross-fostered chimpanzees by bringing them into their home and raised them as human children. And part of that raising as human children was the use of sign language to communicate. So their goal really was to explore not communication specifically, but more about what Veronique's lab is talking about. The goal is like understanding how human a chimpanzee would become if they were raised in a human family. And wow, that really opened my eyes, because there was a lot of things that were very different from what I had heard from the learning field about what than compared to what they were doing. And the main takeaway that I got from this is that there was no learning theory that encompassed everything. So there were these aspects of learning. Traditional learning theory would only deal with very specific experiments and things like that, but there wasn't something at the level of a specific organism. So questions like, why are some things hard to learn for some animals? Why are they hard? And then other things are easy for them. But that's completely different between different species and different individuals even. Why does the enriched environment matter so much? And then going on other levels, what about molecular networks and neural networks? How do these create a learning system through the specific wiring and then lead to the global behavior of the organism? There's a lot of pieces missing here. So each of these questions has been explored in isolation, but rarely is this all put into a global idea of how learning happens in a context of a fully functioning organism. And then if you're going to make a model from the information that we have of learning theory, how does that model even work in the real wild, in the wild? And that question then took me in a completely unexpected direction, because I was thinking about biology at the time. And I looked at sci-fi. And so when you look at sci-fi, you see these amazing robots like what you see from Star Wars and other things. And I say, where are all of our sci-fi buddies? You know, the beings we want are the friends that we see on TV. But what we get is, you know, this mindless automaton that is missing a lot of those characteristics. So today's AI obviously cannot build a full being that we think about on the movies. And why is that? Well, there's really a fundamental difference in the design. So life is flexible. They make instant decisions. There's open-ended tasks. Veronica said that, you know, we don't know everything. And that really makes us lovable in some ways. Where today's AI, it's repetitive. There's just a ton of data processing, and it works really well on narrow tasks, but if you put it in other environments, it fails altogether. This is not lovable, right? So today's robot brain, when you think about it, is a lot of data, big data. There's a lot of computing, cloud computing. So in another environment is where all the computing is happening and then sent to the device. All of this gets put together in a knowledge-based system. But in the end, it's all human defined. A human has defined this. That's not what's a natural learning is, right? So what can we do? How do we bridge the gap between artificial and natural intelligence? And my idea is neuroscience should help fill that gap. So today, at very best, the best AI that we can build is a mimic of human. It's a reflection of humans. But there's no underlying understanding of the biological intelligence that creates our intelligence. So what if we apply principles from neuroscience to help then develop better AI in multiple layers here? And we can start at simple things, even like looking at simple organisms and simple behaviors to first understand the principles. I personally choose to look at the simpler organisms because I think humans are difficult. So I think things other animals can help us solve some of the challenges that humans are not quite as easy to solve. So one of the things I think we need to understand is what's called ethology. And ethology is the study of natural behavior. And there's some terms that come from this biology, such as sign stimuli, and that's things in the environment, stimuli that evoke a specific response from specific animals. And these are not learned. And a famous example is the gull, the herring gull, has this red dot on its beak, and just having that dot makes the chicks do feeding behavior, peck at that dot. And the funny experimental evidence for this is that you can make a super normal dot, like a huge dot, that has nothing that looks like a beak at all, and the chicks will peck at it. So you can really see that it's a dot that the chicks are responding to and not the beak itself. And so those species-specific behavioral patterns from the chicks are sometimes called innate behavior, but species-specific behavioral patterns is a little better term. And these describe what animals actually do and what are the relationships among the behaviors. And these are the kind of questions that I want to know about ethology. So I worked with a scientist by the name of Kevin Crisp at the University of St. Olaf in Minnesota. And we decided to do an experiment to understand these relationships among behaviors. And these are innate behaviors and what happens in specific environments over time. And in his case, he had leeches. And so here's a little video of what leeches do when you put them in a new environment. So the science stimulus here is getting dumped into a new environment. They always start with swimming around. Okay, well, what happens is they have a kind of predictable series of behaviors, but in some cases, it's not all that predictable what they do. So you see, they went from swimming to then crawling across the jar here. And so what we did is we categorized what they did and understood the time that they spend in each of these behaviors and the probability of going from one behavior to the next. Okay? And so I'll show you here what this looks like. So once something happens, then you get into a sequence of behaviors often where you have a very high probability of behavior 1 going to behavior 2 going to behavior 3. But then sometimes these behaviors, there's an equal probability of what will happen next. And this is called a terminal behavior. So in some cases, it's very predictable, the sequence of behaviors that animals will do. And then in other cases, it seems to be just a decision point where anything could happen later. And so we built an algorithm that described this, then to put this variability, first of all, the probabilities, and the time spent in each behavior. And when you put it all together, you can create something that looks very, in an algorithm and put it into a robot, it looks very lifelike. And I'll show you what that looks like. So on the left, we have a toy that's called the hex bug that's just on all the time. And then on the right, we have our little bug with an algorithm that describes the behavior of something like a leech. In this case, there's no sensors. All it has is one actuator that turns on and off based upon this algorithm. So basically one behavior. And you can see the difference in what it looks like to the human eye. So notice it starts and stops, and it appears to solve this maze just because it's starting and stopping and changing direction more easily, right? So that looks intelligent suddenly. And it's only because it's not stuck in one little behavior all the time. It's starting and stopping and exploring new directions just by random. Okay? So that's very lifelike behavior. What if we go to something more interesting? A rat. This is a more, well, for me, it's more interesting. So now let's go to multiple behaviors and then have a series of probabilities to calculate the transitions from one behavior to any of the other possible behaviors. Now, rats, when you put them in an open field, they'll explore the space, but in a particular way, and you'll see here. So you put the rat down in the middle, and they don't really like being in the middle. They'll sniff around, and then they'll go to the sides, and they tend to stay near the sides, right? And notice they have variability in how long they walk for versus sniff the corner versus stop and sniff. They'll scratch themselves. Anyway, so we'll observe the rats for several minutes doing this, and then have several rats and do some statistics and figure out what the model of a rat is. Okay? And then put that into a robot. So now this one appears to have a lot free will in the way that it acts. So the timing of the response isn't random, but because it follows the algorithm that looks a lot more like the behavior variability of a real rat, but it's not quite predictable either. So it depends on the behaviors at the time. So let's see this. So this is just a cute little demonstration here. The different lights on the back tell you the behavior state that it's in. The sensor in the front, it has one sensor that tells distance. And we use that kind of like a nose. It'll move back and forth like it's sniffing. If it sees somebody from a distance, it'll go towards them. If it gets too close, it'll stop. But what's interesting here, all the students, because they figured out that it would come towards them when they could see them, they were all running around trying to get the robot to try to come to them, like calling to it like an animal. Even though it didn't have any hearing, they would still use all the ways that they would interact with a dog or a cat or something. Say like, come here, and put their hands out. And so they treated it much more like a real animal, and it appeared to have free will to them. So let's put that into a little bigger context here. So what we found is that behaviors can be categorized. It's not just individual isolated behaviors, but they seem to have themes, right? So they're overlapping groups of behaviors. So we call these behavior systems. And so some of them, like aggression, has some overlap with sexual behavior. Avoidance has some overlap with aggression. But each of these things have biological relevance to them, right? And there's a hierarchy to the types of behaviors that'll come out, as in, some behaviors are more dominant based on certain situations. And the way that I'm kind of looking at it now, and this is completely my own speculation, is that each of these systems seems to be interacting with emotions, so to speak. And the emotions is something that I would define as kind of a behavioral state. It's kind of a chemical state of your mind. And certain emotions then make for a prioritization system that tells you which types of behaviors are more important to do at the moment when there's a choice. So if you're in a really, let's say, playful mood, you're more likely to get playful behavior rather than aggressive behavior, even if you get, a little bit of pain, like you get slapped a little bit when you're playing rough, right? Where if you were in a scared state, you would tend to run away if you felt anything slightly painful. And so the same stimulus with different emotions gives you different types of behaviors that can come out, right? So there's also a dynamic system to these emotions. So things will be either becoming like more emotional or less emotional. And this happens all the time, right? And so this also directs like what kinds of behaviors are within that system. So the more extreme behaviors, such as, like not just like backing away, but running away, sprinting away, things like that happen depending upon how much emotion there is in the system, right? And so I'll give you a little bit of a demo here. Let's see if can I show this, because this one's a link. How do I show this screen? You can't see the video, can you? Is the video working? Or can you see the, okay. 1 second. Ooh, maybe I don't know, how do I move the sharing? Here we go. Okay, so here's a couple things here. So Watch as the same stimulus changes the behavior because the emotions are changing, right? So if you pet it over and over, it's in one state where it's angry right now, and now you're starting to pet it, it calms down, and it's doing something else. The same touch, if you're in a ticklish state, funny behavior you know about you.
And only serving. Yeah.
So it's casing you in a high emotional state. Here's a learning event. So a sound predicts pain. And now you hear a sound, it runs away from the sound. So that's one event and it learns something. And we see now when it can't escape, it gets more and more afraid of the situation until it can escape. So let's go back to the presentation now. Oops, there it is. Okay, so those are some examples of the escalation and the different behavioral systems in the context of emotions. Okay, how about the learning? So I showed you one event of learning there. That's a Pavlovian conditioning, and hopefully most people are familiar with that, where you have a signal such as a bell that predicts food, and then after pairing it over and over, if you just ring the bell, a dog will salivate to the sound of a bell, where before it didn't salivate to the sound of the bell. Well, with Gardner's research, there was something that really came from that spoke to me, and it turns out that with conditioning, most people are focused on very one response, but it turns out that it's not learning just that single response. It's not just the reflex of salivation. What you're actually learning is you're learning a whole suite of behaviors to the sound of the bell. So anything that's related to feeding in the right context could be elicited by that bell after that point, even if you hadn't specifically taught it about licking or, begging or anything like that. The sound of the bell could, in the right context, then get the salivation, the begging, the licking of the lips, anything food related. So the conditioning seems to happen at a little higher level than just individual behaviors. And this explains something that's kind of non-intuitive. So why are some behaviors easier to learn to others than once you get food? Well, it has to do with how the animals feed. So if you're teaching with food with pigeons, it's easier for them to peck keys because that's how they get their food. They peck for it. For rats, they handle their food. And so for pressing levers, learning about food, pre-feeding behaviors, they press the levers in that context. And other animals, which they thought at first were stupid, like frogs, because they wouldn't press a lever, well, if you look at their ethology, it's because frogs don't manipulate things to get food. They are ambush predators. They just sit there and wait for their food. So they can still learn signals of when the food is coming, but they're not going to press a lever to get food. They're going to wait and then attack. Owls are a particularly interesting example because I talked to a researcher that tried to teach owls to peck keys for 10 years. 10 whole years he'd been working with owls. And he said they never did it. And it's because, well, owls don't peck keys to get their food. They fly in and grab them with their talons. And he described it as like, well, owls are a lot like cats. They don't do what you tell them, they do what they feel like. But in reality, it's because that's not really the way that they want to deal with eating. They use their talons, not their beaks. So what happens then in the sign language world, in the language world, with a chimp, if you try to teach by giving a food reward every time for a sign? Well, they also will get distracted. So instead of learning more about language, you get begging when you try to reward food with sign language or sign language with food. So if you want a conversation from a chimpanzee or a robot or a kid, you don't give them cookies. You need to set up a conversational environment. So that's the main finding there. So previously, I put all of this together into something that kind of encompasses each of these parts. And one part I didn't talk about was the molecular networks. But I put together in those robots an algorithms that had the learning. So it makes this feed-forward conditioning, the emotional systems with the dynamic behavioral systems, and the global regulation. That's basically the emotional state and the increasing and decreasing of how emotional they are, right? And so what does that get us? Well, it gets us a framework for organizing behavior, and it gets you a way of learning multiple behaviors in real time directly from experience. So that, though, is not good enough. We want to do better. So now I'm at the point where I want to make new algorithms with a new product. And this is the next robot that I want to build. We have a design for it. It's time to go start building it. This is what we're calling Pup AI. It's a soft, lovable robot that will have the features of animals that make them actually compelling, both on a physical and intellectual level. And so what I would like help with from people like you is developing algorithms for the learning, the interactions, and then understand what are the consequences in real life of this with the real product. So what needs to be done? Well, I don't think that we can just use a large language model to make this brain, because I don't think that's the right direction. I don't think it's good enough. LLMs are hard and cold. They're repetitive. They have too much reliance on the voice interaction, not enough on the physical interactions and the other things that go with the voice. The LLMs don't learn well from experience because they had to have a big data set and then they have to adapt in real time. And the most important thing for a small companion is that the LLMs are massively inefficient. So they really mostly need either a big computer on board or a connection to a cloud and sending data all the time. And that's just not appropriate a lot of times for kids and for consumer products. So we need new AI strategies. And so here is kind of the three things that I mentioned before that I think that we need to do more work with. Creating a comprehensive behavior model. And I'm not saying a foundation model in the AI sense, but something that gives you information to put into a model of principles of intelligence. We also need a global learning theory, something that works all the time in all situations. And we need to know more about how the lifelike robot that we are building will affect human-to-human interactions and human-to-machine interactions. So how does it affect the connections people make among themselves and among the robots also? So with this case, let's really make a dog. So not a mimic of a dog, but basically a dog personality that's inside. So let's make a framework through the parameters and not just mimicry. Let's catalog all these species-specific behaviors in different contexts, such as the time spent, the probabilities of changing behavior, the variability involved. Let's make a catalog of the stimuli that the dogs actually respond to. What are the cues? What are the environmental factors, such as the social situation, the dominance hierarchy, familiarity with people in the room, and how the dogs play in the real world. Let's make a global learning model. So need to know more about conditioning, like how that happens. So previously, most people have focused on a single behavior when you're talking about conditioning, like how one behavior changes. Well, what about the global behavior? How does it reorganize its behavior in its day-to-day life overall. So things that aren't related to the thing you're trying to teach at all. How does it affect those other behaviors it's not even doing at the time? Does it change the frequency that they happen at other parts of the day? And then how do these behaviors fall into a behavior system or not? How are the behavior systems organized, in other words? Another part with this is about the variability. So, and some people might call this skill acquisition. So how do you go from doing something random to something very specific and the same every time? And then vice versa. How do you go from something where you're doing the exact same thing and be more variable and nuanced in the way that you approach things? And then I want to combine that better learning model into a better personality framework. So how do we get then a dog that learns really well? And the last part, what about the human connection part of this? So what are the consequences with this dog, with the interactions with different types of people, kids and adults? What's it do to their level of comfort, like their well-being is what I mean by comfort, how long they play with this toy, how they interact with the toy itself, and how they interact with other people after reacting with the toy. And what does this mean? Is this a good thing or a bad thing when you actually have these new interactions? So is the robot acting like a human or a pet to this person? And if so, is it a good thing? So one measure might be oxytocin. That's a chemical in your brain that's related to social connection. So if oxytocin is increased when you play with a toy, is this a good thing or a bad thing? We have to figure that kind of thing out, right? And is it mimicking or replacing interactions, or is it building upon interactions with humans? So I would like the goal to be, let's put a product out that actually brings people together rather than isolates them with the product, right? So, would you like to help me? I have lots to do here. And I'd just like to give a little thanks to some of the people that have worked on this. Kevin Crisp in particular helped me develop some of these algorithms. I had a lot of students at different universities, particularly St. Thomas, who did the rat experiments. My company, BrainTobot, I had a team of software engineers that helped build this and do experiments with kids as well. R. Alan Gardner, who passed away a couple of years ago, he really sparked this interest in me. And of course, some of my product testers, some of which were my own kids. The one on the left, the blonde one, is my son Torm, playing with an early prototype. So thank you very much. And do you have any questions for me?